Hello everyone, I'm Nathaniel and welcome to my talk on machine learning of FET PET static and dynamic imaging features for the prediction of treatment outcomes of glioblastoma, and special thanks to my supervisor Martin. And so in this talk I want to give you a bit of background on the disease of glioblastoma and then go into the FET PET imaging features and how they're prognostic of overall survival. And then I'm going to go a bit into machine learning and neural networks and in deep learning and see how we can bring those together within my research. But first I want to introduce you to the field of radiomics that I'll be working with. So the radiomics is the process of extracting large amounts of features from medical images. And so we like to think of medical images as just pictures that we use along the treatment planning process. But when in fact we can mine massive amounts of data from them that we can use to uncover new information on disease characteristics. And so we see potential use for this in FET PET images of glioblastoma. And so glioblastoma is one of the deadliest forms of malignant tumor that a person can be diagnosed with and is classified as a grade 4 astrocytoma by the World Health Organization, and is an extremely aggressive and highly invasive disease of the brain. And so current treatment involves maximal tumor resection followed by radiotherapy and concomitant temozolomide, which is an alkylating agent. And even with this relatively new development in treatment, the prognosis for patients is still grim, with a median overall survival of just under 15 months and a 5-year survival probability of around about 10%. And so currently MRI is the main imaging modality, but we're always looking for new imaging modalities that give us better insight into how the disease works and to give us better accuracy and prediction of treatment outcomes. And so that's where I believe FET PET comes in. So FET PET is positron emission tomography using the radio-labeled amino acid O2-18F fluoroethyl L-tyrosine, which accumulates within the highly proliferating cells of the tumor volume. And so FET PET is suggested to be indicative of metabolic activity within the tumor, aggressiveness, and propensity for recurrence. And so current research has suggested PET scans to be used within the clinic. And so we want them to be used as a complement to MRI, but not as a supplement. And so what we want to do is verify results and standardize our method so we can justify this additional dose to the patient. And so as you can see here, this is just an example of a T1 weighted MRI of a glioblastoma patient that's just been taken post-operatively after a maximal tumor resection. And upon analysis of the MRI itself, the tumor volume was verified as gross total resected. But by looking at a fusion of that image and the FET PET data, we can see that the biological tumor volume was measured as 26 cubic centimeters, which is presumably due to additional malignant invasion within the brain. And so you can already see how we can use this to gain additional information into the disease. And so this is just a look at the static imaging features, usually of the 3D image itself. And for each voxel, we have a standardized uptake value. And we can measure standardized uptake values for the background to represent the normal uptake within the brain. And so we can apply this tumor to background ratio to delineate our biological tumor volume sort of semi-automatically, so that we can only get the tumor volume for activity that we believe to be above a certain threshold given the background ratio. And so from the biological tumor volume, we can get also these other imaging features known as the maximum tumor to background ratio and the mean tumor to background ratio. And all three of these imaging features, these conventional features, have been shown to be prognostic of overall survival. And so moving on to the dynamic imaging features, so this is how we are able to observe how the uptake changes within the tumor volume over time. And so different various acquisition protocols exist, but they usually involve taking data frames at close intervals to begin with to reduce the noise and then increase this interval as we go further after radionuclide injection. And these acquisition protocols usually last from between 40 and 50 minutes. And so we get this time to peak and these time activity curve types, with type 1 being no discernible peak and type 2 being a peak uptake at a midpoint followed by a plateau or small descent, and type 3 being an early peak followed by a constant descent. And so an early time to peak and attack type 3 have been suggestive of poor overall survival. And so an example of this is just over on the left here. We see patient A has this early time to peak with attack type 3, and patient B has a time to peak at around about a midpoint followed by a small descent. And so we would expect patient A to fare worse than patient B. And so now jumping into the machine learning portion of my presentation. So in radiomics, we want to apply machine learning to medical images. And so this involves feature engineering. And so I've been mentioning features a lot. And so features are measurable properties that we believe to characterize our data. And examples of textual imaging features are correlation, which is a measure of how the intensity of the voxels remain the same over a constant area. and coarseness, which is a measure of how the intensities change between different voxels. An example of radiomics in this area of research is this unsupervised cluster analysis by Kabir et al. And so these three clusters are supposed to be completely distinguished from each other given these imaging features that they've chosen. And so this was specifically used to distinguish patients that have pseudo-progression and true tumor progression. And so if we want to avoid doing this feature engineering, which often involves going through hundreds and hundreds of different features and picking maybe just like a small amount as shown here that perfectly characterize our data, can take a lot of time and can inject a little bit of bias into how we choose them. And so we can go to deep learning, which is the application of deep neural networks. And so the benefit of deep learning is that features are engineered by the network, so we don't need to go through this process. An example of this is from a fairly recent paper just published at the beginning of this year, I believe. And this is looking at different MRI imaging modalities for high-grade gliomas. And so you can see the different imaging modalities are here, and they're putting them through these convolutional neural networks through here, which are used for image identification specifically. And they're training them to make these predictions on overall survival. But before they make these predictions here, they take these feature maps that are the automatically extracted features by the network, and they put them into this feature fusion here alongside the demographic and tumor-related features. And they've put it in what's called a support vector machine, which basically draws a hyperplane within feature space that distinguishes and classifies people through a binary classification into short and long overall survival. And short and long was given a threshold value of just given a median overall survival of the patient data set that they were using. And so you might be wondering why they've chosen to cut these out right at the very end before they make the prediction in the network. And so this is what happens in deep learning, where as we create a deeper network and add more layers, we are able to extract higher features. And so an example of this is, just to try and simplify, is we have an image of an elephant that is trying to be identified into a classification within this network. And you can see the network is only extracting these really simple features. These are just very simple shapes. But as you go deeper into the network, it begins to extract these high level features that are closer to how we might look at an image and identify it. And so some of these patterns, we hope within these high level features might be could be invisible to the naked eye if we were to observe an image ourselves. And so this brings us to my research aims. And so we're going to be conducting research on a 24-patient cohort with confirmed glioblastoma that's just been completed at Sir Giles Gardner Hospital. And this patient data set has both 3D FET PET data and the dynamic acquisition protocols that we just discussed. And we're hoping to do, this is the main aim, we're hoping to extract a feature class for a 4D data set using radiomics or convolutional neural networks. So currently in the literature, there are no feature classes that have been described just specifically for a 4D data set. And so if we're able to get these out properly, this would lay the foundation for possible future research for other people and also for myself. And so once we're happy with these features and we get a sort of machine learning architecture that we're happy with, we can use these features to categorize our patient data based on overall survival and possibly progress-free survival, which is an additional endpoint in this study, which is basically from when the tumor reoccurs rather than from when the patient unfortunately passes away. And so once we make that, we're hoping to probably do a binary classification as well. And all of this is additive research into personalized radiotherapy, which I believe to be the future of this a big area of research, specifically in radiomics, where we will possibly be able to adjust treatment plans based on very small things in patients, ranging from biomarkers, different gene mutations, age, demographic data. And so, yes, we believe this to be the first steps forward. And so here's a research map that I'm going to be doing. So we start up here with our 24 FET PET images, and we go to probably what I believe to be one of the more crucial steps in here is the data pre-processing stage. And this stage will be done with help from the University of Wisconsin. They provide us with MATLAB code to extract the information from the provided DICOM files. And so what we want to do here is validate that, the data that we've got is correct and that we're able to put it into these machine learning and neural network algorithms because these algorithms don't know if data is put in wrong. They'll learn incorrect data no matter what. And so we need to make sure that everything is correct before we move on to the next stage. And so here's our 4D data set. And from this 4D data set, we can try our hand at looking at feature engineering, which is some of the features that I was just discussing. We probably have to comb through probably hundreds or even thousands of different features and put them through various algorithms to try and characterize our data well. And so we do that for our textual and dynamic imaging features, and then we can put that into our chosen machine learning algorithm. So we want to choose a machine learning algorithm that's specific for our type of problem. And we can also go a separate route, a bit more of an experimental route to see what we can do with automatic feature extraction here. And so we'll probably have to develop our own convolutional neural network or look to the literature for specific designs to this problem. And so we want to train the convolutional neural network based on overall survival or progress-free survival and extract those high-level features and feature vectors and feature maps, and then also do the very same thing. And so what we want to do, finally, if we're all happy with that, this process might cause us to sort of go, if we're not happy with the architecture, it's not doing well, we might have to come back and go down again also. And we expect this first part to only be done over the summer holiday. I'm hoping to do it by then. And then this is the main portion we're going to focus on to extract this 4D data set. And this should probably take about 6 months, and we'll probably do this in Python or MATLAB. I'm pretty good at Python at the moment, but I'm still got to learn MATLAB, so that's an additional task. And then if time permits, we can have a look at this as sort of experimental route, and which I believe should take maybe just around about 3 months, maybe half the time. And so for this final stage, this classification will be pretty quick. We're just classifying the patients based on overall survival, and we'll do that with a binary classification, as I said, of basically good versus poor. That's basically how this is going through in the literature. And then finally, we would definitely want to do a statistical analysis involving properties such as accuracy of our predictions, sensitivity, which is the true positive rate, specificity, which is the true negative rate, and also implement our 95% confidence intervals into this. This is always expected within these, if we want to publish this to, so people can read them and get a good understanding of how well our machine learning algorithms are doing. And then finally, we want to do publication, which is, I'm sure, the end result for most people. That's about it. Thanks for listening. Yeah, the questions, it might be a bit hard because that is a bit full on. Some of those it talks about convolutional neural networks.
So you're going to take patients that currently have an MRI and you're going to give them an extra PET scan?
Oh, it's already been completed, the study.
Yeah,
so
you give them an
extra dose.
What is your dose of radiation and how do you justify that?
I don't know the exact dose, but we justify it as we've talked about the ALARA protocol in radiobiology, or we justify it through these forms of research. Obviously, the ethics can be a bit of a nightmare because because you just have MRIs, that's no dose, but now you're doing...
Patient A, I'm not so worried about, but patient C,
yeah.
you've got a chance of surviving.
Yeah, just because the disease is so deadly, that probably helps with a bit more of the approval. Yeah. And also, it can also help them, even during that process, doctors can look at these images and also get a better understanding. That definitely goes to help with the justification.
It'd be good to know what the dose is when you present later in case you get asked.
Yeah, I definitely will. I'll look that up probably when I get home.
And I'm interested.
Okay. I'm sure it's in the gigabecquerels that. Yeah.
Is there such a thing as 4D convolutional neural networks? Does it exist in the or multidimensional?
Well,
more than 3D?
See, I was thinking that when we do the convolutional neural networks, we'd have to just do it on the 3D PET data set. And they did make a point, if we can go back here, they did make a point with this that the 3D helped a lot in the prediction process, much better than 2D. There was, I'm not sure. I could possibly look into how they do the deep learning for videos. Maybe that could help. But other than that, if we need to fall back, we can do just a 3D PET data set and just try and maybe just engineer for the dynamic part of it.
I guess because you're looking at such small features like that maybe the naked eye can't see, maybe like I don't expect that there's a control sort of scans for people who don't have glioblastoma and how the brain sort of interacts with their PET scans. So how are you going to try and get around the like maybe just how the brain works and takes up those
Yeah.
nuclei?
As you might know that sometimes convolutional neural networks can be a bit of a black box in terms of the features, and it sort of also depends on how you downsize towards the end of the convolutional neural network. I think they did end up, this fully connected layer, they tried going, so they used the last layer and then the second last layer and had a look at those. These features they ended up downsizing quite far and only got about like 4 features from possibly this these are multi-channels. And so these multi-channels are done in parallel, then concatenated at the end. But yeah, it'll be definitely, this is a bit more experimental. It'll be definitely interesting to see what you're saying. Any more?
Any other questions?
Thank you.